So hi and welcome. I have the pleasure to introduce you to the Flatland Challenge, and then also the pleasure to handing over to some of the top participants who will then present their solutions actually, and then also some more members of our team that are going to present some of the thoughts they had on Flatland also while developing and where it should move from here. So why is SBB playing computer games? Well, it's fun. That's actually one of the reasons. And the other reason is, if you look here, that's the Swiss railway network, and that's real data you're seeing simulated on the traffic. And those of you who heard the keynote yesterday, we have projections that there will be approximately 40% more traffic in certain areas of Switzerland. So we need to enhance the capacity on our network, adding more trains. And adding more trains really means the network becomes denser, so any disturbance you have in your network propagates further. So you kind of need to get a good hold of disturbances early on and kind of manage the traffic such that delays don't spread across the system. So it's very hard to compute this in real time for all these trains. And so what we do today, it's with humans, we look at smaller regions, and a lot of human optimization does this. But we believe that the more trains we have, you have to have a more global view. So this was our motivation to turn to the world and ask, come on guys, do you have some great ideas how we can actually tackle this problem, how we can do decisions on the global scale of the Swiss railway network. So that's how Flatland was born in collaboration between AIcrowd and SBB, born on the whiteboard in our offices, and then developed with people from within SBB, AIcrowd, and some great collaborators from around the world who helped make this a reality. So what was this Flatland Challenge? So the Flatland Challenge is really to generate a traffic management system. And we gave the participants a few possibilities how they can tweak their solution to make the best solution out there. So first was an observation builder. We just gave them this grid world and we gave some basic observations, but we said, well, you can make your own observation. We give you all the data you need from the environment, you can access it and build the observation you think is most relevant for your agent to solve this task. Also, they were able to build predictors, and predictors are ways for agents to tell other agents where they're going. So kind of predicting the future. And this is really relevant for railway because you need to early on detect conflicts. And then of course, one of the main tasks to build a controller to control all the agents. So I'll just go quickly through some of the basic observations that we implemented. So on the left, you see each agent just has a local field of view that turns with the agent. If you look at it, you quickly realize that's probably not going to work out very well because you can only move on the rails, so most of the field of view doesn't even interest you. So happily nobody used that one, but it was just implemented to show. And then you see here on the right side a local tree view, which makes much more sense. Now the agent only observes possible paths it can take. And people built upon this to come up with more clever, and I hope we'll hear some about how we can improve this even further today. And then we set up the challenge to first introduce the participants to Flatland and then evolve and make it more difficult. So the first task was really simple. It's like, we put you somewhere in the grid world, navigate to your target. This was very simple to solve, but it was kind of to getting to know how do rails work in Flatland and so on. And then we introduced multiple agents. And now you also see these kind of predictions that they are making, and they are avoiding each other, they're avoiding future conflicts. So also here we got very good results, and then we said, okay, so let's bump it up a little bit more. So we added now different speed. It's not animating, unfortunately. Maybe I can. Okay, there we see, yeah. So now many more trains, different speeds, so that became a bit more complex. You had now also not only to avoid conflicts, you also needed to optimize which train goes first. So this is a very hard task to solve. But we got some really great results. On here. So this is the leaderboard standing at the end. And from these top 5 solutions, actually 4 teams are here and 3 teams are going to present their solution. And because it's so great and I'm so excited to hear what they have done, I'm just going to hand over now. And we'll start with solution number 5. Thank you very much.
Okay, hi everybody. I'm Evgenia. I come from the Etc. machine learning team, and I'm here to present our solution that got us to the 5th place. So I first want to say thank you to Netcetera, which allowed this to be one of its machine learning projects. We also have experience with many other real-world projects, for example, face detection, insurance fraud, Eiffel Power Challenge, cost estimation, and so on. We have experience with many specialization, and we wanted to add reinforcement learning there too. So we thought that this challenge is going to be a great way to do so. These are the people that were involved in the challenge in any way, usually in brainstorming sessions. So we had 3 NetCetter employees and 4 interns involved into the various stages in the challenge. So we built a reinforcement learning solution. We have the environment, which was particular railway setting with agents and targets. The trains were the agents. We had a clear reward structure at the beginning, and we built a DQN model, which took state of the agent observation that Erik showed previously, and outputted the action that this train needs to take. So the question now I want to answer is how to represent the state of the agent. We tried many different things. We tried local observation, tree observation, cache shortest path, and decide that the best thing to do was to look at the 2 shortest paths from the next switch. Best in terms of quality of the solution and plus time complexity, because it's not easy to compute at every point for each train what to do next. So for this yellow train here, it needs to go to the station to the left. These are the 2 shortest paths that we are looking to. So how each of these shortest paths implemented? We describe them with observation vector. We put many different things in the vector. So we have information about the other agents, so who else is on my path, what are their speed, what are their direction, is there possible deadlock, potential conflicts, statistical info about the path, and so on. So in total, we had 40 features for each path, and in total, for the 2 shortest paths, the size of the state was 80. The action size was 3. For each timestamp, we chose if the train should stop or take the first or the second shortest path. So this was our first attempt to build a solution. What happened? The agent did not learn anything. So they just get out of the station, got into the deadlock. It was really easy to get into the deadlock, and plus the deadlock is really costly because look at this red square here. If the deadlock happens here, then all of the agent needs to take a pretty longer path to get to the 2 neighborhood cities here. So what we did, we thought about 2 concepts. First, we add more information about the deadlock in the observation vector, and then we guided the search with the priority in the beginning. So the agent knows if it has a priority or not, and should he go or just wait for the other agents. So how is priority computed? For each time where there is a conflict on the path, we built a graph where each node represents 1 agent, and each in the graph represents that there is a conflict between these 2 agents. So we built a graph, and the question now is how can we decide from here which trains have priority or don't. So we tried many heuristics to solve this kind of graph coloring problem, because it's clear that 2 neighborhood nodes cannot have the same priority one. The best solution was to choose the node with highest degree. So in this example here, we have 2 nodes with degree 3. We choose one of them randomly, for example this, and then all of the neighbors need to have priority 0. And that the algorithm is repeated until all of the nodes have their priority. Of course, we need to make some sanity checks here. For example, malfunctioning agent shouldn't have priority 1, or agent who has its path block, and so on, but it worked pretty good. So we improved our result a little bit, but there were still problems that we need to solve. So we played a little bit with the reward structure, and plus we gave some more information in the observation vector. So we introduced penalty for each step because we need to tell the agent that they need to take the shortest path. We gave more information about the trains behind them. So for example, this yellow train only sees the shortest path in front and is not informed that he's blocking other trains. And also we need to control where the agent actually stops. So this is how our reward looked like. There was a large positive reward for getting the agent into the station, a large negative reward for getting to deadlock, and all of these smaller penalties for various things that we want to correct, for example, not following priority. The only other decision we need to make was how to build this environment provider, meaning on which environments we will train our agent. So the best idea was to introduce levels. So in the beginning of the train process, the agent learned how to get to their station, and then the difficulty of the levels increased, and the agent learned more complex behavior. So to conclude, we had 99 agents done in the first round and 55 agents done in the second. It was really hard to find the parameters that work, so we had a lot of idea that we want to try next. So I really hope that the challenge continues and we have more rounds. Thank you, and this is the email where we can reach us.
Hi, my name is Vitaly Bondar, and I will present second place solution of Flatland challenge. I made it with my friend Roman Chernenko. We all come here to listen something about reinforcement learning, some fancy stuff, some improvements, some, I don't know, tricking in actor critic. Sorry guys, we even not tried it, had no time. This is the high level of our approach. First, we do some initialization. We create our own graph, whereas each vertex is a railway cell, and edges is possible directions. It's conditioned also by the train orientation. It's important. Also, we pre-calculate shortest passes for each train to its target from each position and orientation path. Then environment starts, and on every step we check if there are any malfunction. If it happen, all started train need to be rescheduled. We do it one of two algorithms I will cover later. And then all trains continue its plan, and new train checks if there are any new passes. If it finds it, it starts on next step. For single agent environment, you can handle only special information, obstacles and so on. But for multi-agent environment, everything becomes harder. You need to know where other agents will be in exact time. So we created our own space-time data structure where we keep information for each cell and on each time period. Is it occupied or it's free, and who occupied it? So how we find a path for every train? We just used A* based algorithm with rollbacks. For heuristic, we take travel time to the current cell plus wait time on the current cell and minimal possible time to the target, which was pre-calculated on initialization. So then for every train, we calculate best path one by one. When we know all passes of other trains, we can calculate new path for a new one. If you will look on the image on the left, you will see that here is obviously two solutions. And it depends if you start with red train or with green train. It's good to find some optimal order of handling these trains, but it's still in our wish list. So we just handle first the fastest trains, And among the same speed trains, we handle first trains which is closest to the target. When we have all this shiny plan for far future, Malfunction broke everything. It's obvious. So what shall we do? We add invariant to our plan. It's an order of passing cells by the trains. For example, on rightmost cell, first goes green train, then blue one, and then red one. Then we try to make some naive solution, some rescheduling to keep this invariant. And if some trains need to wait, okay, let's it wait, like this red train here. For sure, it's not optimal, but it's recover our space-time data structure. It become valid again, and we can handle trains. So then we can just go one by one for every train that was changed, calculate new passes. If new pass shorter, we just change plan for this train and receive better result. Red train can go first. But that's not all. Flatland has a very bad thing that if you start the slow train, you can't wait anymore. You need to wait up to 4 ticks. And if fast train malfunctioned, then slow train will continue and broke our invariant. You can't recover it anymore. Here, same problem, but on bigger part of the world with the red and green trains. So what we do in such situation? We try to move every train as far as we can, not to break this invariant. And if next step will break environment, we just stop this train and say, it will wait here forever. I know passengers will not like this, but at least we again recover our space-time data structure and it's again valid. So we can again go one by one for each train and find some solution how to unblock it. Here, very important, the order of handling trains. So how we find this order? We made a graph of trains where each edge is a blocking. It's ordered edge that train A block train B. Then we make topological sort of this graph and we receive some order that if we process trains in this order, hopefully all trains will go that way. We'll find how you see on the right image. That's main ideas in very high levels that we used in this competition. Thank you.
So, hi everyone, I'm Mugrel. I'm a software engineer at Google, but I have to say that participating in this challenge has nothing to do with my work there. You have to add this disclaimer. I mean, I participate generally in optimization challenges because I like them as a hobby. And I will present my solution. Actually, first of all, I want to thank actually Vitaly, because he actually the details of the high-level details of my solution are very similar to theirs. I just did it better, right? Because my score was something like 99% of agents reaching their destinations compared to 96% for their team. So I guess the interesting part will be, since I didn't have time to add any kind of, I have text, right? But I didn't have time to add, nice images and stuff. That's why I also want to thank him again, because all the nice details I were presented, and now maybe I can focus just on the differences, the things that really were different. So there were, similarly to the previous team, 2 main components in my solution. One is to actually generate or regenerate paths for the agents over a time-expanded graph. This is the same thing as the space-time data structure, if you want to call it like that. And the component that, when a malfunction occurs, then it tries to update the path in order to restore the invariant, right, that is required for regenerating agent paths. And also to try to somehow avoid deadlocks and, to bring the system back to a consistent state. Right, this is, again, very similar to the previous team. I'll try to focus more on the details rather than, the high level again. So, precondition for regenerating agent paths is that they don't really generate from scratch, so each agent needs to have already a feasible path over the time-expanded graph. Yeah, the time-expanded graph is, just, it basically has a node for every cell and time. This is similar again to the previous theme. This worked because there weren't that many cells and the time steps were also limited. So there's at most 2,560 time steps. I actually used a bit more to actually let my agents, most of them to reach some solution, even if that would be over the allowed deadline. And actually, there are actually not so many cells, right? It seems like the environment is big because they can be 150 by 150, but actually there are never more than 3,000 cells. This I also verify locally by generating many tests with a sparse local rail generator, whatever it was called. Okay, so what this component does is, again, it starts with an initial set of feasible paths. Initially, every agent can be just simply outside of the environment and wait there. So basically, that's also a feasible path. Then tries to improve them. And the main steps are as follows. I run this algorithm up to max runs. I'll explain maybe later what these parameters mean. At each run, I use a number of threads. Most of the time, I just use one for easier development, but in my final submission, I actually used 3. And each thread generates a number of permutations of all the n agents. In permutation order, take the agent, remove its path from the environment, from the time-expanded graph, and then find a new one using some A-star style, algorithm. This is, again, very similar to the previous team solution because I also pre-computed distances from every cell and every orientation to the target for every agent. And I also have the waiting time as part of the heuristic and so on. So this is very similar. I would say maybe I'll focus on a bit more details later. What's different? So for each permutation, once we go through over the agents in order, each agent gets potentially a new path. It can be the same one as before, right? Because that was also a valid path initially, so it will continue to be a valid path. And the set of paths is now stored, right? And the best one is kept. If there's an improvement over the initial set of paths, I go to the next round. Otherwise, nothing happens. I will just stop, right? So it's not always that all the runs are used. How do you score a set of paths? Obviously, the most important metric is how many agents actually reach the destination. This tiebreaker, it's a sum over their time to destination, right? Over the agents that actually reach it. I tried various scoring functions. Most of them were of the form time to reach destination at some exponent, right? And there's some. I mean, the value of exponent that worked best in the end was actually 1, which is the same. It corresponds to the reward function that was anyway, basically returned by the environment, so it didn't really change much. But yeah, I tried to be smarter. It didn't really work. Now, about generating permutations. Actually, this is, I think, an important part. I think, the previous team only considered the single ordering, in which, take agents, first of all, in increasing order of this, decreasing, whatever. I mean, the highest agent, the fastest agents first, and then so on, the slower one afterwards. I think they only consider them into some fixed order, depending on the remaining time to destination. I try that. That is not necessarily the best way to do it. The best thing is to try random. Basically, try within a speed group, just randomly shuffle the agents. And of course, because we generate multiple permutations like this, some of them are better than others. Using the heuristic as time to destination, it was tried as one of the permutation, but in the final submission, I just removed it because it didn't bring anything. So, why this actually worked? Actually, initially in my first submissions, I was trying the other way, basically trying to put slower agents first, because my intuition initially was, I thought, okay, I have to, because they are slow, let's put them into the environment first, so that they have time to reach the destination until the final deadline, until the final number of time steps. But that was actually bad because they were slow and they were also malfunctioning, so they were blocking other agents. So it was better to actually put the faster agent first, because they would also get out of the environment faster. And then once an agent is out of the environment, it doesn't malfunction anymore. So it doesn't block anything. So it was actually much better to just reverse this ordering. Okay, the shortest path for a single agent, as I said, it's similar. It's an A-star style algorithm. Now it tries to minimize just the time to reach the destination, so it's nothing fancy. It has a tiebreaker. It doesn't really matter so much, which is, if an agent is not already in the environment, it tries to add it as late as possible, given that it reaches the destination at at the minimum time, it tries to keep it in the environment as little as possible, right? That is the intuition. I could put it in the beginning, and then it will have a lot of waiting in the environment and block other agents, or try to put it a bit later, and then it will block a little less. And yeah, for agents that are already in the environment, this algorithm only considers states where they can make a decision. So if they're already executing an ongoing move, then first I simulate until the move ends, and only then I start this algorithm. So I think this is not something very special compared to the previous team. I mean, okay, I use in Vermont, I think, all the rules that are available, by the simulator. Actually, this was actually maybe a lot of headache on my side that I actually got the first non-failing submission, because I added a lot of asserts in my solution to make sure that I understood how the environment works. So I was having something like, okay, I plan a path like this. I expect that once I make this action, I perform this action, the new state is like this. And then, expectation didn't really match reality. So, it was a lot of banging heads against walls, figuratively speaking, until I actually, learned all the rules. Some of them are simple, like, an agent can reach a cell at the same time as another agent leaves it if the whatever ordering of agent IDs is increasing. It's possible that more agents reach the same destination cell at the same time, but as long as they arrive in increasing order of their IDs, because once you enter the destination, you actually disappear immediately, and things like that. There's an extra that I'll actually talk about a bit later, which is about trying to avoid or to minimize deadlocks. I think, as the previous two teams already mentioned, actually this is the biggest pain in this competition, avoiding deadlocks. Yeah, this was also, my, this is the part that I had, the biggest problems with. Okay, I'll discuss about this a bit later. Now, second component. Let's say, yeah. I have to cut it short?
Yes.
Do I have any 1 minute or at least? Yeah. No? 1 minute, perfect, okay. So, after a malfunction, I try to use the same algorithm as before, to try to keep the visiting order the same, it's the same as the planning did it. But, I'll skip all the important details, but the problem is that this would work if we could pause agents when they have ongoing moves. The problem is that, if an agent started moving, we cannot stop it. This can cause deadlocks, but only when there are two agents both moving to the same destination, both moving to the same cell at overlapping times. So one way to actually avoid deadlocks is to just not schedule such agents. So option 1 was to allow deadlocks. This actually worked reasonably well. Option 2 was to avoid deadlocks altogether. This is actually easy to do in the planning space, but it was too conservative. And option 3 was to avoid most common cases, basically nested time intervals. Yeah. And the important part that I have to say is that I actually had an important bug in my shortest path algorithm during most of the competition, which I only found towards the end, and it was about 0.7% worth. And because I ran out of time, sorry for that, the algorithm is just various parameters so that everything fits within 8-hour time limit. Okay. I'll skip about the unexplored ideas. I think this presentation will be shared. So thank you.
So you'll notice already that my presentation is kind of the opposite to Mugarel's. It's just like loads of pictures. So I mean, I was working on the Flatland environment with AIcrowd and SBB for the last year, and I did some of the sort of rendering kind of work. And so towards the end, I was trying to illustrate some of those ideas with kind of graph theory. So why use graphs? Basically because to try and reduce the complexity. I mean, some of the other presenters have already talked about their graph ideas, and so it's really that's what I did, and I used some of the basically the graph graphics libraries that you can get, like sort of 3D force graph things, basically in sort of JavaScript. So basically, it's kind of exploratory data analysis, EDA stuff. So why use graphs? Oops, where are we? I'm a bit confused by the screen here. Those are some of the libraries I used. There's a guy called Vasco Astoriano who is on GitHub and does some sort of very clever animation things. So why use graphs? You've seen these sorts of things already. So if you do something naive like that, then you're going to break the rules when you sort of go around the corner there. I had the way that I sort of resolved that, what I wanted was a sort of a static representation with like a single graph representing the whole thing. And so I came up with this, which maybe looks a bit complicated, but basically just got extra nodes and sort of directed edges to represent the different directions. The directed edges are, or the directed edges, the direction nodes are tied together by sort of grid nodes, which represent kind of resources, which sort of are, the things that have to be locked. So that was basically how I did it. And here's a sort of zooming in. I hope you can see the little moving dots there, but it just kind of represents the constraints or the semantics around a junction there. The fact that these guys coming from the north can get a choice. So these guys coming down here can either go that way or that way, whereas going up that way, the two different routes sort of coalesce. And now, of course, the shortest path works. So you can just use a simple shortest path algorithm straight out of Network X, was the Python graph library that I used. And then the next thing we want to do, obviously, is to sort of take out the long paths, and I collapse them down to a node. So rather than sort of an edge, I kept a node. That may not be the best way of doing it, but it seemed to sort of work in this just the diagrams that I did. So here's the sort of the classic thing. We've got these sort of agents on either side. I've done it sort of the fairly sparse representation. So there's some nice long paths to contract there. So if we create it with lots of all the nodes in there to begin with, and then the next, which kind of looks like, sorry, this is Vasco again. So that's all of those little nodes there, just turned into a sort of a 3D force graph. It's the animation here. This isn't live. It's just like a moving GIF. So then we sort of do the contraction, and that turns into something a lot sort of simpler. Now we're sort of looking at something that looks at the right sort of level of complexity, maybe still a little bit too complicated, but similar to the complexity of the problem. And then it is you can see the little mouse moving around. So this is the sort of thing that you can do with Vasco's JavaScript library. That's the same thing in sort of 2D with the little animated dots there. So yeah, then this is just ideas that I think you've already heard from the participants. Just how to generate alternative paths, and just something that occurred to me was the fact that, well, they do sort of seem to recombine, but I think you could potentially use this as a sort of an agent observation. The agent doesn't need to know about the recombination. So here we just kind of nip through how the sort of we've got these two agents who are going to sort of collide in the middle. One wants to go left, one wants to go right. We can generate these alternative paths using that sort of deviation kind of approach, which sounded very similar to Evgenia's approach. There's the two paths. So okay, now we want to detect conflicts. I'm on 5 minutes. That was only 5 minutes. Erik we used up some time plugging the computer in. So all right, so we need to detect conflicts, and those are on the sort of on the grid nodes rather than the sort of edge nodes. I claim independently came up with this diagram. Turns out that SPB have got a similar one, a kind of animated version of this already. So we just kind of, the agent kind of navigates across the thing there. Create the sort of nodes down here, and then you get this nice sort of step effect. There's one agent. There's if we introduce a second agent. Clearly, they're going to collide in the middle. This is all very visual and easy it looks very easy, but of course it gets more complicated when you've got more of them. There was a little scheme here for how to detect that they're going in different directions. I think it's kind of fairly obvious. So now, okay, it takes an alternative path, and now the resource diagram shows that bit in the middle he's going using a different resource. I did. Now where are we? Oh yeah, I did try to represent these things to do a clever sort of 3D. Where is it? I've forgotten. Vitali, was it, did a sort of space-time diagram, and I did try to do a space-time kind of diagram. But in the end, I thought that it was kind of too, it was too visually confusing. But, you know, maybe we will do another version of it. But so we've got the resource representation. It's a deadlock detection, various ideas for other things that needed doing. Just to show you that the thing kind of works at scale. And shortest path. This was K shortest paths. This is the deviation effect, kind of, you know, exploring a little bit more around taking longer alternatives. That's a network version of that. Oh, yeah, I like the word hammock for the thing. So rather than a tree topology, it's like a hammock topology because all the paths end up at the destination, right? I better go. And here's the thing at scale again. So this now we sort of see the combinatorial complexity of the thing. We've got the sort of the space, time along the x-axis, resources down the y-axis, and there's this sort of detection thing, deadlock detection. I guess I have to skip through this. So there's the libraries again, if anybody's interested. There's a bit of, you know, the problems I had trying to join JavaScript and Python together. In the end, it wasn't too bad. And that's a summary. And I've got one piece of eye candy at the end, hopefully. Hooray, there we go. So that's the 80 by 80 sort of environment with the sort of the paths contracted and in one of Vasco's displays. Thank you.
Yeah, I will be fast. So I really find all these solutions super cool, and this visualization really makes the problem even more tangible. So I guess now a lot of you want to just try it out, right? Like try with the environment, experiment with your own ideas. So this is my goal. I want to give you a quick getting started with Flatland. Actually, now you've been exposed to a lot of the core ideas of the environment already, so that will allow me to go a bit faster. So here is a typical small Flatland environment. This is a grid world. You can see why. It's actually split up into squares that we call cells. The idea is that only one train can be in a single square at one time, as you heard before. There are 10 different possible cell types. Here you see some of them. And what they define, actually, depending on the cell type, it will say which transition is possible. So when the train is in a given cell, where it is able to go next. So the goal for the train is to reach the station. You can see that as a fairly typical reinforcement learning environment setting, right? So you provide an action, which is what the train should do, and in return you get an observation, a reward, and a completion indicator. Now, of course, in most cases you have more than one train, right? So this is actually a multi-agent reinforcement learning problem, multi-agent environment. From a technical point of view, it doesn't add much complexity. You just handle that using dictionaries. So for each train, you have a unique handler, unique ID, which are the numbers here, and you can just define which action each of those trains should do. And when you get the observations, the reward, etc., you can just get that indexed normally. So let's have a look quickly at the action space. Trains don't have so much freedom actually with what they can do. Depending on the rails they are on, they can either do nothing, which means actually keep doing what they do. If they were running forward, they will keep going. If they were stopped, they will stay still. If they are at a dead end, this is a special case where they will actually turn around. Move left is basically that they will deviate left if there is an intersection that will allow them to. Going forward, moving right, and stopping. If you want to perform an action which is not allowed, it will simply not do anything. Now, more complicated, as you heard before, is how you handle the observations. Actually, coming up with good observations that allow you to solve the problem is an integral part of the Flatland challenge. As you have heard, you have multiple solutions using global observations where you just get all the information. It's as if you had some kind of control center that was taking the decision from a central point with a bird's-eye view. You have the local observations, which are not so efficient because typically you can have a train which doesn't see the target where it should go in its local observation. And the tree approach that you've also heard quite a lot before, where the idea is to leverage the underlying graph structure of the environment. So here is typically how you would extract a graph structure, a tree structure from the grid. So you would start from the train, check all 4 possible directions. On every time that you have an intersection, you would add a node in the graph with all the possible directions that you can follow up to. So the easiest solution would be to just take this graph, compute the shortest path, and just have the agent follow it, right? And this actually works quite well if you have only one agent. But the problem is that as soon as you have multiple agents, it's not so simple anymore. You start having deadlocks. Okay, so you've seen solutions for that already when the participants talked about the solutions. Another aspect that maybe you are not so familiar with is how you generate the environment. If you want to actually experiment with it, you will want to generate a variety of environments, some which will be simple, some which will try out cornercade, and some who will be larger to see how your solution scales. Here is the simplest solution to create an environment. You basically just define it by hand. Here you can see that you have a 6x4 array of tuples. This will basically create a 6x4 environment. The first number of each tuple maps to the type of each cell. And then the second number is the rotation clockwise of the cell. So here you can see the result. And typically you can see the one that is circled in red. So it's type 2 that is rotated 90-degree angle. It's quite straightforward. But obviously, you will not want to create everything by hand because when you want to consider a larger environment, it would become too cumbersome. So for that, you have a number of methods provided, which basically will create the environment randomly. And you will basically define some specification, and it will create it the way you want. So here is an example, for example, with a sparse rail generator. By tweaking the parameters, you can see that you can get various looking environments. Now, so far, we've only been considering some kind of idealized railway network, right? But we all know that in real life, these things are not simple. So we can make it more realistic by introducing 2 extra complexities. One is to have trains with a different speed. As we have heard, this makes things harder because if you have a slow train behind a fast train, this will cause problems. So this simulates the fact, for example, that a freight train is slower than a passenger train. It's actually one of the main difficulties when operating a real railway network. There's a problem, network perturbation. For example, when I got here, my train was slightly delayed. I heard there was a landslide in Pridu, so this is the kind of thing that can happen, or just harsh climate conditions. So here is how you would tweak all these parameters, depending on what you want to test. You can see, you can just define the ratio of train with a given speed that you want. You can also adjust the malfunction, how much of the agents will malfunction, the minimum and maximum duration of the malfunctions. So if you want to dig further, I invite you to consult the documentation. We are currently completely revamping it. The goal is to have very clear, well-organized notebooks that you can take one at a time, open them one click in Collab or Mindbinder, and just start experimenting right away with us. It's not ready just yet, but it will come very soon. For now, you have the documentation at this URL, Flatland docs, AIcrowd.com, and here is the address of the URL of the challenge. Thank you.
I wanted to say what SPB will keep doing with this. I'll do that briefly, but mainly I just want to thank all the participants and all the collaborators, open source collaborators we had. It's a really cool experience also for us at SPB to be working with people around the world who are contributing to this with their insights, and they helped us really make this a really cool challenge, and this is going to live on. So it's not over. This Flatland challenge is done, but Flatland will be kept, and we're keeping on developing it further. And thank you very much, Florian, for all the work you did in the last few weeks, also ramping up all the documentation, helping us bringing this to the next level. And also what you realized, we had to cut most of the participants short, so most of them could not even tell all the ideas they still had to be explored. So we're very happy to hear that, and we believe the same, that there's so many more ideas we should explore, be it in reinforcement learning, operations research, algorithms, or combinations of the two. So stay tuned for more progress coming here and Flatland going further. At the SPB side, of course, we're now interested to go from this simple, more abstract environment to a more realistic environment. So we have within our company other simulation softwares where the details of the physical world are a bit more close to The simulation is more close to our real world. I can illustrate this, for example. So instead of each agent just having some fixed speed, we can actually simulate the physical properties of a train. So the engine having a restricted power, and so even though it wants to drive a certain speed, it might not be able to because it's too steep and so on. So this adds a lot of complexity to the problem again. That's why this will be kept for future solutions. And then, of course, we want to map it not just to randomly generated environments in Flatland, but to the actual topology that we have outside. So there's lots to come. So we're happy still to keep collaborating with the world and developing this further as a cool multi-agent reinforcement learning problem and like a playground to test new algorithms and to compete with a long-standing operations research algorithms that are really good, but also have their drawbacks where we believe reinforcement learning can help overcome some of the troubles. So if you want to try Flatland for yourself, not only online at the SBB booth upstairs, we have made a game out of it where you can control the trains by hand. There's Flatland stickers to put on your computers if you like. And I think I'll hand over to you now, Mohanty, and for the rest of this track. Thanks a lot. Oh, yes, of course. If I have time, I'm very happy to answer any questions regarding Flatland or SBB.